1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... What can we multiply each term by to get the next term? 1/2. 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8, and so on. Does that make sense? Anytime we have a series where the terms are generated by multiplying by a common multiple like this, it is a that is what defines a geometric series, when there's a common multiple to jump from term to term. We call it the common ratio. If you do a term and divide by the previous term, you'll get it. Like this is extra scratch paper work here. If we do 1/2 divided by 1, that equals 1/2, obviously. That is the common ratio, R. And you can do it with any two terms. If we do 1/8 divided by 1/4, multiply by the reciprocal, the 4 divides 8 twice, it reduces to 1/2. Any pair of terms you choose, 1/16 over 1/8, 1/4 over 1/2. Any two consecutive terms, take the second one, divide by the first, and you'll get this common ratio. And they will always be the same. If it's a geometric series, it will always be the same. So for this one, we'll say that R, the common ratio, is 1/2. Here's another example. 2, 6, 18, 54. What is the common ratio here? 3. So 6 divided by 2 is 3. 18 divided by 6 is 3. 54 divided by 18 is 3. Again, any two terms, take the second one, divide by the first. Any two consecutive terms, second one divided by the first, will give us that common ratio. Now, we've already seen a little bit with this one. Remember when I divided the square up? We actually started here. 1/2 plus 1/4 plus an 8 plus 16. It all added up to 1, didn't it? Even if you took it all the way out to infinity. So if that adds up to the 1 plus this one, this is going to all add up to 2, isn't it? This is an example of a geometric series that converges. That will converge to 2. You add all these infinitely many terms up, it'll get closer and closer to 2. If you carry this pattern out to infinity, what's that going to do? Diverge. Those are going to add up. You're going to go to infinity. That sum is going to go to infinity, isn't it? So this is an example that converges because that will have a finite sum. This is an example that diverges. So again, for geometric series that we're looking at right now and telescoping series that will come after we finish geometric, we can actually find the sum, but later on, after those two are finished, we're only going to be asking the question, does it converge or does it diverge? Which one of these is it? That's the question we'll be asking. Let me point something out here. This is like 2 times 1 plus 2 times 3. 2 times 3 is 6. Plus 2 times 9. 2 times 9 is 18. 2 times 27. So that is like 2 times 1 plus 3 plus 9 plus 27. Right?
Why?
We can, if we want to, we can factor a 2 out. If we want to. Sometimes we don't want to, even though we can. And that's gonna be the case with one of the telescoping examples.
Why is it, why is it not just like the beginning term times 3, and the one above it, why is it not just times 1/2?
Say, wait,
So instead of,
this is not connected to that up there.
right,
Separate example.
right, but like the second one, it's just multiplied by 3 going forward, isn't it? Yeah.
Yeah, 2 times 3 is 6,
It's on the
6
back.
times 3 is 18,
Right, right,
and
right.
so on. So, but we can't divide a 3 out of the 2.
Okay.
This is like,
Okay, never mind.
does that make sense?
Yeah, yeah, I see what you're doing.
But these are all divisible by 3, I'm sorry, these are all divisible by 2, so I pulled a 2 out of each one, and now I just factored a 2 out of the whole thing.
Okay.
So the reason I show you that, you don't have to write this in your notes, it's gonna come later. But when you have the sum of, as, you know, k goes from 1 to infinity, of something in here, 2k, you could, a constant multiple inside can be factored out. Okay, that's not the same as this, but that's what's happening there.
Okay, I see.
Does that make sense? That's why I wanted you to see that. Okay. Any questions about these 2 examples? Any questions about the r equals 1/2, the r equals 3? Any questions about those? Notice inside here, 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, and so on. We good with those? All right. Here comes another one. This is still geometric series. We're gonna do a lot with this. This might take up the whole class. Here's another one. 0.9 plus 0.09 plus 0.009 plus 0.0009 plus dot dot dot. Can anyone tell me what R would be without actually doing any calculations, just looking at it? Divided by 10. So let's not think divided by 10, let's think multiplied by 1/10. Does that make sense? Yeah, multiplied by 1/10, or in decimal form, 0.1, which is 1/10. Because when we multiply by 1, it moves the decimal to the left. When we multiply by 0.1, it moves the decimal to the left 1 position, correct? So this decimal times 0.1 moves to the left and gives us 0.09. Multiply that by 0.1, moves it to the left, and we get 0.009, and so on and so on and so on. Looking at that pattern, will that converge or diverge?
Converge.
Converge. And just looking at the pattern, what will it converge to? Yes, it will converge to 1. This equals 0.9 with a bar, meaning 0.999999999 forever. And that limit, as the number of 9s goes out to infinity, approaches 1. Okay, so you're correct, this would eventually converge to 1. But we're going to see some math to do that. All right, so any questions about what a geometric series is? The terms are generated by multiplying by a common ratio. Some of them converge to the sum, meaning after you add them up, that sum, even though you're adding infinitely many terms, will sometimes converge to a finite limit, and sometimes it will diverge, go off to infinity, right? Yeah. Okay. Now it's going to start getting very mathematical. So in general, we can say that a geometric series, the sum of the first n terms is equal to a plus a times r, the common ratio, plus a times r squared, because, where do I go here? We multiply this times our common ratio to get that. Then we multiply by the common ratio again to get this, so multiply by r 2 times to get that, which made it squared. Does that make sense? Then it will be cubed and ar to the 4th, and so on and so on and so on. So let's go ahead and write let's leave it like this. Plus, dot, 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 plus, and I'm going to write this as ar to the n minus 1. This would equal the sum as k goes from 0 to n minus 1 of ar to the k power. So when k is 0, r raised to the 0 power is 1, and you get a. That's that. Next time around, k is 1. A times r to the 1 power is ar to the 1. That's this. Next time around, k is 2. A times r to the 2nd power. That's that. And it goes on and on and on and on. Until you get to the last one up here, n minus 1, which is here. You guys okay with this notation? Got what that all means? All right, watch this. This is really cool. Let's multiply everything in here. I'm not going to worry about that, but let's multiply everything in here times r. Distribute that r all the way through. Then we're going to get r times s sub n equals ar, a to the r, plus a to the r squared, plus a to the r cubed, plus dot, dot, dot. I'm going to write this as ar to the n minus 1, so that's not the last term, but the previous to the last, plus ar to the n. So when we multiply this one by r, we get that last one, because r to the n minus 1 times r, you add the exponents, the ones cancel, and you get r to the n. This is the one before this that's sitting here that we didn't show. Okay? Now, let's subtract all of this. So we're going to get s sub n minus r s sub n. And look what's going to happen. Remember, we're subtracting, so all of these become negative. These are going to cancel out. These are going to cancel out. This is going to cancel out with the next term here. Everything in between is going to cancel out. These are going to cancel out. And we're going to be left with this, which is going to be negative. We're going to be left with this one did not cancel, and that last one did not cancel. A minus a r to the n power. You guys okay with that? Now, on this left side, let's factor out s sub n. I'm going to factor out s sub n, so I'm left with 1 minus r. And on the right side, we're going to factor out the a, and you're left with 1 minus r to the n. Let's now solve this for s sub n. So we're going to divide each side by divide each side by 1 minus r, and we have s sub n equals a times, oops, I want to write it like that, times 1 minus r to the n over 1 minus r. This is the formula for a finite geometric sum. So if you want to add up the first 50 terms, this formula will do it. Let me make that in just a little bit better.